the following one from Professor Pierre Gressens, that is the head of INSERM, one of the most well-known and authoritative research institute in France. And so Pierre is a good friend and a great researcher. And so he will try to introduce the Grand Gala, the Grand Round we will have later with Stephen, speaking about understanding brain development of preterm babies with huge experience on this field. Pierre, thank you so much for accepting the invitation.
Thank you, Lucas. Thanks for the introduction and the invitation. I'm going to share my slides. Is it okay like this or not?
Yes, we can see the slides.
Okay, great, thanks. So I will try to, in 20 minutes, to give you, of course, be a bit superficial overview of the developing brain in the preterm infant and why we believe that these mechanisms which are taking place might be impacted by prematurity and lead to some of the long-term consequences. One first thing which is important to realize that the preterm brain is not just a small adult brain. If you look on the top left, you have a 25-week brain, and the bottom right is the adult. It's still far from it being just a small brain. It's very different. There's still a lot of things ongoing, which probably makes the preterm brain very fragile and very vulnerable to a lot of environmental insults. If you take a term brain, it's still different from an adult, but it starts to really look like a smaller adult brain, but very different from a preterm brain. And indeed, if you look at different organs, of course, in a preterm brain, which is the orange vertical rectangle, you see that many organs are still immature in a preterm infant, but they are much more close to the end of maturation compared to the top list, where you can see that even almost close to term, but especially preterm infants, you can see still a lot of things are ongoing, making, again, this brain very vulnerable. It's probably also true for the lung, as you know, but some other organs are much closer to the, maybe not the final mature stage, but still getting closer compared to the brain, which is still a moving target compared to many other organs. Just as to put in a framework, as you know, the two major consequences of prematurity is cognitive impairments, as shown here in an IQ measurements. If you are born below 32 weeks, and the more you are born preterm, the higher risk you have to have lower IQ. It's even worse for the boys compared to the girls, like many disorders affecting the developing brain. And the other one, which is emerged more recently, these preterm infants are also at risk to develop, here is shown ASD, but a lot of psychiatric disorders as they grow and mature during their life. Even the adults, they can acquire psychiatric disorders like depression at a higher risk rate than control-term infants. And we have learned from other disorders, and ASD, for example, is not a destructive brain damage, it's more a maldevelopment. And it's the same for preterm infants. We have moved from probably the last 20, 25 years from very destructive lesions like cystic PVL to more subtle changes in the brain architecture, closely linked to maldevelopment, so changes in the normal steps of brain development. Rather than killing cells, it's really abnormal programs of brain development, which of course in terms of neuroprotection, it's a completely different game. It's one thing to prevent a neuron from dying. It's another thing to make a neuron to make the right connections. So it's probably much more complicated, even if the neurons are still present. Having said that, I'm going to show you only two MRIs. We had a wonderful talk about the imaging of these baby brains. We still have, in some cases, but they become more rare and rare, we still see some destructive lesions, destructive lesions, which is probably the end of the comet of the cystic PVL, which has almost completely disappeared, luckily enough. So we still see a few destructive lesions, but it's very rare and very focal. We're not even sure that they have a major impact on brain function because they're very discrete. But on the other hand, it's a kind of an old picture now, and we have seen much more beautiful pictures. We see a more diffuse white matter changes, which is not, again, not destructive. The white matter is there, but the microstructure is not normal, at least in many of these preterm infants. It's a risk factor for long-term negative outcome. So again, we believe that these changes in white matter is again linked to maldevelopment and not to destructive events. It's a big complex slide, but one key hypothesis now is that one key factor leading to this maldevelopment is inflammation. We've moved from a purely hypoxic ischemic concept towards a more multifactorial situation. And among these multiple factors, inflammation, systemic inflammation is probably very important. And in fact, these preterm infants are exposed to multiple reasons to have systemic inflammation. It can be before birth, chorioamnitis will lead to systemic inflammation. It can be during birth, hypoxia and hypoxic ischemic events will lead to systemic inflammation. Mechanical ventilation will lead to lung and then systemic inflammation. Of course, sepsis is a source of systemic inflammation. And later on, a neck is also a major source of inflammation. Luckily enough, not all the preterm infants get all of them, but very often they get more than one source of inflammation. And epidemiological studies have shown us that the more protracted, the more sustained the inflammation is, the more risk you have to have adverse outcome. And this can be demonstrated, this inflammation, by increased inflammatory cytokines in the cord blood and the blood, and through endothelial cells. Many studies post-mortem, but especially experimental studies, have shown this activation microglia is really responding to this systemic inflammation. Microglia being the macrophage of the brain. This leads to neuroinflammation, and this will lead to different steps. I will show you some examples leading to brain maldevelopment and the later consequences in terms of brain functioning. So we really believe when others say inflammation is really a key factor leading to brain maldevelopment in these preterm infants, at least some of them. This is a bit of a zoom in of the different steps of brain development which are taking place in the preterm infants. The red rectangle is a grade prematurity between 24.5 weeks and 32 weeks. And you can see that among the major steps of brain development, most of them are still occurring when the baby is born preterm. The only one which is completely finished is the production of neurons, at least the excitatory neurons. But we'll see later on that many of the other events are still taking place and can be influenced more or less by prematurity for different reasons. So if we go back to microglia, why do we believe that microglia is important? When we another looked at the development of microglia in the brain of human fetuses, these are postmortem cases. This is a coronal section, this is the cortex, this is the white matter, lateral ventricle here. From reasons which is kind of obvious, microglia get into the brain, many of them through the choroid plexus. Then they swim in the ventricle, then they invade the parenchyma, and then they populate progressively from the ventricle to the meninges, the complete brain parenchyma. But unfortunately for preterm infants, just because of timing, you can see the dark dots which are microglia, zoom in here. Many of them, or most of them, are located in the white matter, where we know a lot of things are going on in preterm infants. And indeed, he's comparing on the left side a normal fetus. I mean, normally, of course, there was an abortion, but for non-brain reasons, you can see the white matter. If we focus on G and H, is the microglia staining. You can see a few ramified resting microglia in the control fetus. Is a preterm infant on the right side of the same age, so 26 weeks of gestation. You can see the many more microglia, and they're running, which is a sign of activation. So because the cells are the wrong place at the wrong time, if there is something ongoing, like systemic inflammation, these cells will get activated and will probably hurt or damage the white matter. So it's just a matter of timing. And that's probably why we don't see so much of white matter damage in term infants, because at that stage, the cells are distributed homogeneously in the whole brain. As I mentioned before, gliogenesis, which is production of astrocytes and oligodendrocytes, is also extremely active in the preterm brain. I won't talk today about astrocytes, but will also play a role. But especially the oligodendrocytes, which are the cells which are very important because they will produce a myelin, and without a good myelin, you don't have a good functioning brain. And this, in a preterm infant, as we know, we have learned from neurobiologists, these cells will go through very immature progenitor to the fully mature cells, which is the only one we can produce myelin. But in between, there are intermediate stages. And in preterm infant, we have mostly these two stages of the white matter because they're still maturing. And we know that these cells, unlike the difference from the mature cells, they are very fragile, especially they can be destroyed or hurt by hypoxia, for example, and by inflammation. And now we have learned that at least nowadays, these cells don't die anymore. In the past, they were dying because the insults were much more severe, but they don't die, but they get stuck in maturation. So instead of moving from this stage to the finally producing myelin oligodendrocyte, they get stuck, or at least they get delayed in the maturation. And so this will lead to a delay in myelination. And something which is important in the developing brain, time is money. If you do the right thing, but if you do the wrong time, the function might be strongly impacted. And we believe that delayed myelination, even at the end of the day, the brain will be probably correctly myelinated. It's too late. And so there will be consequences for the functioning of the networks. Until 5 or 10 years ago, we were thinking that all the neurons were already in place before, in the cortex before preterm birth, so that migration was not affected by prematurity. More recently, some postmortem studies have shown that, in fact, intern neurons, not all the neurons, but intern neurons, which are the inhibitory neurons, which are very important for networks, are still migrating until term, probably, maybe even after birth. So, of course, in preterm infants, we have now described, we and others, that many intern neurons are still migrating. And if you have to understand that neurons are produced close to the ventricle, and they have to migrate through the future white matter to reach the cortex. And the white matter, as I showed you before, there are microglia. In normal brain, microglia are resting, they're silent, and neurons can migrate easily. In an inflamed brain, these microglia become crazy. They produce all kinds of factors, cytokines, ROS, etc., which might have an impact on these poor neurons, which have to go through like a minefield. And indeed, some recent postmortem studies in preterm infants have shown that some specific subsets of intern neurons, like the calretinine or calbinding positive intern neurons, which are very important for plasticity, are missing, or at least they are strongly reduced in density. So indeed, in preterm infants, because intern neurons are still migrating, when the baby is born preterm, they might be impacted in the migration. It's when they're missing, this will be long-term consequences of brain functioning. Once the neurons are in place, they have to connect to each other to make networks, which are very important. They have to produce axons and neurites. And again, there is a specificity of preterm brain. This is a coronal section on the left with a histological staining. We have the post-mortem MRI showing you the more classical picture we are used to see. But you can see here, and this is a zoom in of the cortical mantle. On the left side, we have the ventricle. On the right side, you have the meninges. And the blue segment on the right side is the cortex. So very thin compared to term infants. And you have a big pink part, which is a transient cellular layer called the subplate, because it's below the cortical plate. And it will disappear. It's only present at the time of prematurity. And term infant, it's almost gone. And these cells are very important for connectivity because all the axons which are coming from the thalamus and which will go to the cortex and are very important for sensory integration later on after birth, all these axons will get stuck for a few days to a few weeks. They will make synapses with these subplate neurons, and then they will remove this synapses, grow again, and reach the cortex. And so we know now that this subplate is very sensitive to preterm birth. And so we probably have a lot of events occurring there, which might impact negatively this process, which seems to be very important for the thalamocortical neurons, axons, to know where they have to connect into the cortex. And indeed, this is a study from David Edwards' group in London. When they look at connectivity of preterm infants compared to term infants, all the red regions have reduced connectivity, and most of these regions were thalamocortical connections. So there seem to be, again, because of the timing and because the subplate neurons, which are only present at this time and might be affected by preterm birth, this might have a significant, very significant impact on connectivity, especially from the thalamus to the cortex. One final step, of course, when the axons reach the neurons, they have to make synapses, which is, of course, where the information will go from one neuron to the other. We have learned for many, many years now, at the beginning, it was a hypothesis by Jean-Pierre Changeux, but now it's been confirmed over and over. When the brain makes synapses, it's not very specific initially. It will connect too many neurons, which is called a transient redundancy. It's probably an easy way to connect many neurons with not too much thinking. And then, because then afterwards, because of the environment, all the synapses will be used. The ones which are used are probably useful, they will be reinforced, and the ones which are poorly used will be eliminated. And this process is extremely important. If you have too much elimination, your brain will not function correctly. If you have not enough elimination, even transiently, it will be the same issue. So we've learned, at least from animal models, that this process is extremely important, and the time is also very important. And this is the number of synapses in a non-human primate brain. So some people have counted zillions of synapses in the brain. Phase 1 is first trimester, second trimester, third trimester of birth, so first 2 or 3 years of age, and then later on puberty, and then we are all here. So we have a decline in our synaptic density. And we can see that first 2 trimester, almost nothing is happening, but as soon as we enter the third trimester, which is when preterm baby are born, you start to see a very explosive production of synapses. And of course, the postnatal environment is very different from in utero, many more stimulation, etc. And we know that this stimulation will impact the production and stabilization of synapses. So we can imagine that, of course, this process might be strongly disrupted in preterm infants, again, because they are born at the wrong time. Again, timing is very important. And I will finish with this slide just to say, and this was already very nicely discussed and presented before, the brain is not isolated. The brain talks to, we have heard about the microbiota and the gut. I'm not sure it was mentioned, but we have more neurons in the gut than in the cerebellum. So it's a huge number. It's like a third brain, many, many neurons which talk to the brain itself and vice versa, and also other organs, the lung, the hormones also. So the brain is not isolated. I think we have to think in a broader manner to try to not just think of the brain in the preterm infants, but to try to integrate, and with the new technologies, I think it will be the future, to try to see the interaction between brain and the other organs and vice versa. And I will stop here and thank you very much again.
Yeah, can you hear me?
Yes.
Well done. Thank you so much for your excellent talk, and very nice as usual. Is such an important field to understand the major steps moving from the importance of the white matter, the subplate zone, the maturation or the stop of the maturation of the oligodendrocyte. I know I shouldn't speak about, so in the meanwhile we read the questions. I shouldn't really speak about finalistic things. But if I remember well, there were something happening as well in the number of immature oligodendrocyte increasing. It is something like understanding that the brain does know if the oligodendrocyte do work well or not in a way. So there is some signal to produce more of these cells that at the end of the day, they're not working. And I'd like you to ask a question about similarities in between the white matter problem of premature babies and the adding problem of the intrauterine growth retardation as well. So in this sort of complicated link in between the two conditions, the vulnerability of preterm white matter and the vulnerability after a baby has been in a state of intrauterine growth retardation. Never ask easy question, sorry.
The first one, we know there is a crosstalk between the electrode activity in axons and the maturation and myelination by the oligodendrocyte. So if one goes wrong, the other one will go wrong as well, and vice versa. So it's a very intertwined crosstalk. Also, we know that astrocytes and microglia also talk to oligodendrocytes. And so if a microglia and or astrocytes go wrong, the maturation of the oligodendrocyte will go wrong as well. So it's a very, the more we look at it, the more complex it becomes. It's kind of similar to what we see in multiple sclerosis during the remyelination events. There are a lot of similarities, even if its age is very different. But it's an interplay between neural activity and inflammation as a big word. We still don't understand completely the crosstalk, and especially the molecular signaling, on which we could have an impact eventually. For the comparison between prematurity and IUGR, there are a lot of similarities. There are very few postmortem studies, so we mostly rely on animal models when I say there are similarities. We know that in IUGR, you start to see also neuroinflammation, and especially after birth, because there is a big switch. Very often it's a problem of perfusion, and so it's like a chronic hypoxia. And the chain from chronic hypoxia to normoxia, it's an oxidative stress event, and this leads to neuroinflammation. So even if the origin of the inflammation is different, we probably end up with a common neuroinflammation in both situations. That's why a lot of the neuropathologies, not exactly the same, but there are a lot of overlap between the two conditions. Yeah.
Thank you for your answer. So I'd like it, in the meanwhile, we're waiting for the kick off of the grand round. Even people connected from the panels of the speakers to ask a question as well, if you're happy, or anybody else in the room that is already warmed up to ask questions is more than welcome to ask questions to Pierre. So any question? Because I can't read now very well the questions there. Any difference? Seems yes. Don't know. Yes, it's Stephen Miller would like to ask you a question. Please, Steve. Yes.
Pierre, wonderful to see you, and thanks for the amazing talk. You're going to make my job much easier after all of the neuroscience. Wondering if you could say more to your hypothesized role for subplate neurons, particularly given the overlap of where the subplate should be and where we see this burden of punctate white matter injury.
A very good question. Thank you. Not so many people have looked in animal models on subplate, because subplate in animal models is very small compared to humans. But we have done a postmortem study, and we showed the same activation microglia in the white matter and subplate. So we could, if we didn't have the staining, we couldn't determine if it was subplate or white matter, while the cortex was very different. So there seemed to be a behavior, at least in response to an inflammation, which is extremely different between cortex versus subplate and white matter that seem to behave the same way. So despite their neurons, it's a subplate. In terms of neuroinflammation, it's more like white matter. It's maybe why we see, and you see on the imaging, more lesions in the subplate, like in the white matter versus cortex, because for some probably molecular reasons, they are more like white matter-ish structure. Yeah.
Thanks, Pierre. Any other question? I'm going back in the direction of the question I probably asked you. I can't remember how long ago, maybe 20 years ago, maybe in the same direction of Stephen. We always so worried about the differences in between the back and the front of a preterm baby. And so do you see any different kind of vulnerability in that way, according to, you know, I mean, you mentioned the subplate for visual stimulation are already very active, and subplate frontally, they're doing a different job more than acquiring data for the brain, and they're still in the process of organizing themselves to make a connection. So I've always been fascinated by the differences in between the, how to say, more forward maturation of the posterior brain compared to the frontal ones.
It's a very good point, but I'm not sure I have the answer. We know, especially from animal models, there is a rostrocaudal gradient of maturation. So the frontal matures a bit earlier than the occipital. And we know the timing is important. So maybe the sensitivity of the frontal versus occipital might be linked, in part at least, to this gradient. Unfortunately, in human studies, because the brain is so big, and even if it's small compared to an adult, but in terms of histology, most people, including us, we are focusing on the frontal lobes because we cannot compare everything. Having said that, one of the reviewers asked us to look at other regions. So we did occipital lobes, and in terms of histology, at least, we couldn't see very much difference compared to frontal lobes. So despite there is this gradient, we couldn't see in terms of reactivity of microglia, astrocytes, etc. Yeah, if you didn't know which block you were looking at, you couldn't see a difference. Yeah. So at least from what we know from neuropathology, we don't have the answer to your question. But I'm not sure it has been looked in much details. Yeah.
Thank you. So I'm not anymore able to see the 11. I am not anymore able to see the 11 question. Maybe if you can open, there are probably 2 or 3 for you. Down, if you go down, where is the 11 in red?
Yeah, so there was a question about the preoligodendrocytes and the oxidative stress. At least from in vitro studies in the past, we know that these cells are extremely sensitive to oxidative stress and even kills them. In terms of maturation, I'm not sure there's a lot of studies on them, but it's very likely that it's true as well. So I would probably say yes to the to target oxidative stress to improve maturation of OPC, oligodendrocytes, right? Why white matter injury is decreasing and INH is increasing? What is INH? IVH maybe? No, I don't know. Is increasing in premature newborns in Europe. I'm not sure I understand the question because I'm not sure what INH, I don't know what it is exactly. But what I can say, I think one of the main reasons why we have seen an improvement of or at least almost disappearance of cystic PVL is the improvement of the care in postnatal and perinatal care. So there's been a major improvement, or the steroids, all kinds of care. But despite that, we have reduced significantly the CP rate, but we have not decreased the cognitive and the psychiatric deficits, unfortunately. Yeah, I think those are 2 questions which were related to me. Yeah.
Okay, so we are about to be on time.
Okay,
Thank you so much, Pierre. Really
thank
thanks.
you.
Anyone else from the panel that would like to ask questions to Professor Pierre Gressens? Before I thank you so much, because I knew we had a very busy, extremely busy afternoon. So thanks to everybody.
Andy, to
Yeah, I hope
to
the future
put probes and things like. Yeah.
yeah, you are like there are many ways of studying sleep. You can study
Rita Silveira is asking.
yes, you can
Is
study
asking
sleep
the question.
you can study sleep at different level using behavior. You can use the video. You can put many data. It's true that if you have EEG, and now you can really use very small electrodes. If you have EEG, you can really correlate brain activity to the behavior, and this is a lot really of the information. But now in the future, probably we could have many other way of monitoring sleep, simply in looking at video, behavior, and put it all together with all, for example, all the new techniques that integrate many sensors. You can have information about sleep also if you look at the heart rate variability. There is a strong correlation between different brain state and heart rate variability. But what we are missing is to merge everything before in order to understand what's happened together.
Yeah, this is a field for artificial intelligence too. Right. So thank you so much for your talk. And I would move on.
Must be studying with the new knowledge that we have more and more. As I show you, the group of Vanatalo, they are doing a lot of job. But indeed, if you look at the paper of Vanatalo, there is so many information there. And so you really realize that we are very far from understanding your big question. What is really sleep? Imagine also all the other state we don't speak about, the transition state. What is it? So again, for us neurophysiology, this is extremely fascinating, but we realize that we know much more than before, but not really so far from Kursi Daskalova, and so we have really to do a lot of work on that.
If you are happy to reply, there is a very practical question saying, can you perform sleep evaluation extremely birth weight infants in the NICU, and how to do it? We can reply from my side that there are different initiatives together with the EEG. So it's not only EEG studying sleep, because of course it's not so.
Thanks.
Thanks to you again. And